In this puzzle, an object is being fired from off the ground and it is going to strike a target we know that it takes exactly 3 seconds for the object to reach the target. Now, let's list all of the things that are known, or better still, before that, let's do our correct step, which is setting the origin and the axes. I will set rightwards as positive and upwards as positive, and I will set the endpoints. The point at which it was released will be the starting point, that'll be my photo 1, and the point at which it's just about to strike the target is going to be photo 2. Now, this is a two-dimensional problem. So let's list all of the things that we know. First things first, we know the acceleration because this is occurring on Earth. In x, the acceleration is 0, and in y, the acceleration would be negative 9.81 j hat meters per second squared. We do not know the displacements. That's actually what we're solving for in this question. But we were told that the time was 3 seconds. And finally, we are told the initial velocity. The initial velocity is 50 meters per second at an angle of 30 degrees. Now that's a velocity which has been given to us in polar, so we need to convert that into rectangular. So this would be v initial y, and this would be v initial x. So v initial x is equal to r cos theta, which would be 50 cos 30 degrees, which is 43.3. Meanwhile, vi in the y direction would be r sine theta, which would be 50 sine of 30 degrees, and that'll work out to be 25. So now we have 3 pieces of information in both the x direction and the y direction, and we can solve for the displacement. In the x direction, the displacement is going to be given by v initial times t plus 1/2 a t squared, which is v initial, that's 43.3 times time, 3 seconds, plus 1/2 a 0 times t squared, which is 3 squared. But of course, this entire last term is going to go away. So 43.3 multiplied by 3 gives us 129.9. So 129.9 meters is how far this object traveled before it hit the target. And in the y direction, we can do the same thing. Delta y is equal to v initial times t plus 1/2 a t squared, which is 25 times 3 plus 1/2 times an acceleration of negative 9.81 times 3 squared. So 25 times 3 plus negative 9, let's do it like this, 0.5 times negative 9.81 times 3 squared is 30.85, or let's call it 30.86. So the displacement in y is 30.86 j hat meters. In this question, we have someone who is shooting an arrow on top of a cliff. The arrow is going to initially travel upwards and to the right, reach its peak, and then strike the cliff somewhere over here. Now, the interesting thing about this question is that part A and part C are concerned between what happens when this arrow is launched versus when this arrow lands. However, part B is asking about the peak. So what we will do for this question, first of all, we will set what our photos are. Photo 1 will be at the point of launch. Photo 2 will be at the peak. Photo 3 will be at the point of land. We will do the question in the order part A, then part C, then part B. I will set the origin at the launch point. I will set rightwards as positive and upwards as positive. Now, let's work out what information we've been told between photo 1 and photo 3 in the x and the y directions. So, displacement, initial velocity, final velocity, acceleration, and time. Now, we were told that the time for the arrow to land is 4 minutes. The acceleration is 0 in x because it's in projectile motion, and negative 9.81 in y, again because it's in projectile motion. We were also told the initial velocity in polar. So we were shown that the arrow was launched something like this. So this angle here was 60 degrees, and the initial velocity in polar was 30 meters per second. So because this is in polar, we need to break it into x and y. We need to translate it into Cartesian. So this is v initial in y, and this is v initial in x. So v initial in x is going to be equal to r cos theta, which is equal to 30 cos of 60 degrees. I don't even need a calculator for that one. That's going to be equal to 15. So v initial in x is 15. V initial in y is r sine theta, which is equal to 30 sine of 60 degrees, which is, okay, this one I can't do in my head. So 30 sine 60 is 25.98. By the way, when I'm writing it like this, I'm assuming that you know that there's going to be an I hat over here and a j hat over here, and what the correct units will be for all of these different quantities. Time obviously will be in seconds, velocity will be in meters per second, acceleration is going to be in meters per second squared, and so on and so forth. So, now that I have this information, let's go on to part A, where we're looking for the displacement between photo 1 and photo 3. So we have a time, we have an acceleration, we have an initial velocity. So for the displacement, we can use toolbox equation number 2. First, in the x direction, delta x is equal to v initial times t plus half a t squared, which works out to v initial, 15, times time, 4, plus 1/2 times acceleration, 0, times t squared. This entire last term is going to go away, so you're left with 15 times 4 is equal to 60. What about delta y? Delta y is equal to v initial times t plus half a t squared as well. So v initial, 25.98, times time, 4, plus 1/2 times acceleration, 9.81, times 4 squared. So this is one where we probably want our calculators. 25.98 times 4 plus 0.5 times negative 9.81 times 4 squared. 25.44. And of course, this would be I hat meters, this would be J hat meters. So now we have solved for the displacement of the arrow between photo 1 and photo 3. Now, the next question we will attend to is part C. Part C was asking what is the landing velocity of the arrow. So what is the velocity of the arrow a nanosecond before it makes contact with the cliff? In the x direction, you don't even need to do any calculations because acceleration is 0, which means that the velocity must stay constant. And it's probably better that you don't do any calculations because this way you don't run into the chance of making any mistakes. This will just be 15. But in the y direction, things are a little bit more interesting. So we have an initial velocity, we have an acceleration, we have a time, we are looking for final velocity. We can use toolbox equation number 1 to solve this. So Vf minus Vi is equal to acceleration times time. Vf is unknown, minus Vi is 25.98. And all of that's equal to negative 9.81 multiplied by 4. So, negative 9.81 times 4 is negative 39.24, and that plus 25.98 is negative 13.26. So, negative 13.26 j hat meters per second is the velocity of this arrow just as it strikes the cliff. So much for part A and part C. Now let's look at part B. Part B is examining the motion from photo 1 to photo 2, from launch to peak. So we were looking for what the peak height is. That's the unknown in part B. But many of the other quantities are the same as what they were in part A. So for example, the acceleration will of course be the same. The initial velocity will be the same. And one other piece of information. When you're at the peak, the vertical velocity is always 0. So we have two velocities, acceleration, and we're looking for a displacement. There's only one equation that weaves together all four of those quantities, and that is toolbox equation 4. That is v final squared minus v initial squared is equal to 2 times a times delta y. So v final squared is 0 minus v initial squared is 25.98 squared is equal to 2 times negative 9.81 times delta y, which is unknown. So 25.98 squared is 674.96. So this entire left side is negative 674.96 is equal to negative 19.62 times delta y. So divide by negative 19.62, that gives us 34.40. So that is the displacement of the arrow as it reaches its peak. And if you wanted to get its height, you would add to that displacement the initial height of the arrow. In this question, we are told that a person is going to jump with an initial speed of 9.5 meters per second, and they're doing a long jump. They want to get as much range as they can in a long jump. So in this question, photo 1 corresponds to a nanosecond after the person has jumped, and photo 2 corresponds to a nanosecond before they land. Now in this question, the person can be treated like a projectile. So we have to account for displacement, initial velocity, final velocity, and acceleration. So the acceleration, 0 and negative 9.81. The initial velocity we have not been told, but we can infer that because this is a long jump and long jumps always take place on level ground, the displacement in y must be 0. So what about that initial velocity? Well, the launch looks something like this. They jumped at 9.5 meters per second, and if they want the greatest range, that means that they have to get launched at 45 degrees. 45 degrees is the angle that always gives you greatest range. So now we have a velocity vector expressed in polar, 9.5 at an angle of 45 degrees. That's a polar vector. Let's start converting this into rectangular. We have v initial in y, so that's going to be our sine theta, and this over here would be v initial in x. So let's do this conversion. V initial in x is equal to r cos theta, which is equal to 9.5 cos 45 degrees, which equals 6.72. So v initial in x is 6.72 I hat meters per second. Now v initial in y is given as r sine theta, which is 9.5 sine of 45 degrees. Now it just so happens that sine 45 and cos 45 are the same thing, so this is also going to be 6.72. So now we have three pieces of information in the y direction, and we're looking for the range in the x direction. This is easy enough to solve. We just need to solve for the time using the y information, and then use that time to find out the range, that's delta x, in the x direction. We have displacement, initial velocity, acceleration, and we're looking for time in y. So how do we work that out? The only equation that weaves together those four quantities is toolbox equation number 2. Delta y is equal to v initial times t plus 1/2 a t squared. So v initial is 6.72 times a time, which is unknown. Delta y is 0 plus 1/2 a is negative 9.81 times t squared. So you could solve this out using quadratic formula if you really wanted to, but this is easy enough to factor. I can divide both of these terms by t, and when I do that and simplify a bit, I can move a few things around also, and I will end up with 4.905 times t is equal to 6.72. So what I did is half of 9.81 is 4.905. I moved this term to the other side, so the negative sign becomes a positive sign, and then I divided both sides by t. So I end up with a t squared becoming a t and a t going away. So the time is now going to become 6.72 divided by 4.905, which is 1.37 seconds. Now it's very simple to figure out what the displacement is in x. Delta x is equal to, we can use the same equation. V initial was 6.72 times time, 1.37, plus half acceleration, 0, times time squared. But that doesn't really matter because this entire term is going to go away. So 1.37 times 6.72 is going to give us 9.21 meters. So that is the displacement of our long jumper, 9.21 meters.